Alrighty. Well, happy Thursday. So we've got a little bit of stuff to go through here. So let me pull up the syllabus again here. So we got recursion. We've got our next project. We ran out of time on Tuesday to talk about it, um, and then talk about next week. So uh, there's not actually a lot of stuff when it comes to templates that we have to talk about. The template topic is big, but if you look at the Zybooks, because everybody's reading ahead, right? It's okay. I get it. There's only two sections. So I think we can push some of recursion to Tuesday because recursion's a bit of a big topic and jamming it in all today might not be all that great. And then Tuesday we can do a lab on recursion, right? And then we can kind of bump the template stuff a little bit to the lab on the 11th. I think that'll work out pretty well. So it's okay. We'll make it work here. And then we got the midterm coming up still after break, middle of March. We're not there yet, and we still have snow everywhere. So we'll talk about recursion. We'll talk about the project to get started. We'll hit recursion more next week, and then we'll finish up templates. We can probably start templates on Tuesday. I don't know if it's going to take the rest of the time to talk about recursion, but I want to show you a couple of cool recursion topics, and we'll do some more advanced stuff, and we'll practice it in lab. Have some fun with it here before we get into templates. So this should go pretty well. I think then we're still on track for 313 and 327. So we got almost a whole month for the final project. I think we're off by like 2 days. If you want it on Tuesday, I'll give it to you on Tuesday, but I doubt people will start early. Can I be honest? We'll have some specific requirements. It'll have to take you so much time. You'll have to show me work on so many days here. But I think it'll work out well with, minus 2 days there. So it should be pretty good. So we're going to talk about recursion. Ideally, you would have talked about this um, a little bit in 150. If you didn't touch it at all, that's okay, but hopefully you looked at it a quick little bit here. So the really quick basic definition of recursion is a function that calls itself. That's it. So at some point, this function calls itself, and it has to know when to stop. So when we talk about recursion, in order to know if we can solve a problem with recursion, we have to be able to identify two things. You have to be able to identify if there's a base case. That's our technical term for the problem is solved. I know the answer. There's no more recursion that has to happen. That's our base case. So you have to know when it's simple enough to solve. Seems kind of straightforward, but again, that can be a little complex in practice. But we'll look at a couple examples where we could define that. And then the second piece, which is the harder piece, is can you take a problem that's not solved, a complex problem, and make it one step closer to the solution? Can you approach the base case here? Right? If we can do those two things, then it might be possible to solve with recursion. Now, recursion's cool, and it's very useful for a limited set of things here. It's not a nail we're going to use for every single problem. It's a very specialty kind of tool, but for those problems, it's amazing. So if you just imagine your file structure real quick, like if I go open this up here, open my folder in File Explorer. If I wanted, yeah. Goodness, I didn't plug in. Oh man. Okay, thank you. It's on the recording at least, but yeah. Did not plug in the HDMI cord because I'm stupid. Thank you. Let's try this. Hey, there we go. Okay, so my folder, right? If I wanted to write a program that said how many files are in this folder and its subfolders. Well, to do that, we have to look in the folder and find if there's a subfolder, look in that subfolder. 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 Because we don't know how deep this is going to go. You can go folder after folder after folder after folder after folder. You can go nuts, right? Like my path here is already 1, 2, 3, 4, 5, 6 folders long. Now 7 folders long, right? Sure, that's 7. Not too bad here. But recursion makes this easy because I don't need to know ahead of time. I just keep on repeating. If it's a folder, open it and look for files. If you find a folder, open it and look for files. If you find a folder, open and look, like the exact same process over and over and over again. Eventually, the base case is there's no more folders, right? Eventually, someone got tired of saying new folder, new folder, new folder, new folder, new folder, right? And we'll have run out. I don't know how long it's going to take, but that's a very easy thing that's solvable with recursion that is much harder to do without recursion. Because how do you keep a list of all? You can keep a list of all the folders, and then you have to add stuff that you find inside of that one, and you can do it. It's just much harder. So recursion is a easy way to tackle some problems. And our focus for this class is going to be backtracking. There's other kinds of recursion that are not just backtracking, but backtracking is the focus. It's a very practical, easy example for us to look at here for recursion. But for the first one here, we can have countdown. Countdown. This is a pretty classic example here that takes an int for, I don't know, number here. So the first thing we want to do is identify our base case. So if number is 0, then we're going to see out blast off and an end line. Okay. If it's not 0, then we're going to see out the number, and then we're going to recurse. We're going to call countdown given the number -1. Right? And now it might make sense, and I'm going to think about it now because I've done this before, but if you give this a negative number, are we ever going to reach our base case? No, we'll just run forever. And that's not what we want here. I think it actually crashes on us if I remember right here. So if we call countdown of like -1 here, I think eventually it crashes. Let me try it. Count. Oh my goodness. Count down. There we go. I think it'll crash on us. Build errors. Uh-oh. Oh, countdown must return a. Oh, it's not an int function here. It's a void function. That's my bad. There we go. There we go. Hey, we broke. Stack Overflow. Hey, have you heard that word before? Stack Overflow? Is there like a website named Stack Overflow? It might be named after something. Who knew? So, yeah, we broke it. We have too much recursion and the computer can't handle it. When we start talking about memory in the stack and memory on the heap, right, we're limited to what we can put in the stack. And every time we call this function here, we have, this is my call stack here, right? Every call to a function goes on your call stack. Right? It's in the stack here. So C++ has to track this. Your operating system has to track this here. So it knows, hey, this one here, this one here, this one here, this one here. And each one of these, you can look at what the number was. Hey, right now it's 1368. And this one here, the number was 1361. And this one here was 1327. Right? So it has 1,300 something function calls on the stack. And eventually it overflowed. We ran out of memory in the stack. We broke it. So just be careful here. So like less than or equal to 0 might make some sense here. Right? Or you could even add a check and throw an exception. Like if you give me a negative number, tell me I'm stupid. Like you can't count down from negatives. Sure, we know you can, but you're just going to confuse people. Right? That sort of thing. So, but if we do it the right way, right, we get, 10 here. We'll see. Oh my goodness, we broke it. What did I do wrong here? Oh, this should have been an else block here. I was doing this and then doing this again. Right, sorry, that should be else. If we reach the base case, we're done. If we don't reach the base case, then recurse here. Just, I did that on purpose to show you, right? Obviously. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Fantastic. So if I put a breakpoint here, we can see, again, the calls on the call stack. So I'll see, hey, there's 10 calls here to countdown. At this point, it was 10. At this point, it was 6. At this point, it was 2. Right? So what is happening in memory is the values are being tracked here. So there's a memory cost to using recursion because every time you add a function call, that has to get tracked. You have to know what line you're on and what the value of all those variables were. There's a little bit of a memory cost. So this would be much better here as just an iterative function that's just a loop. Right? Much more memory efficient to just make this a loop here. So this is countdown iterative. That takes an int number. And we can just say for int, I don't know, current equals number. Current is greater than or equal to 0. Current minus minus. Right? Do you guys ever do minus minus loops? I feel like they're not as common, but yeah. And all we do is see out the number. And then line, actually, this should be greater than 0, right? And then at the end, once that loop is done, we can see out blast off. I'll just copy that line here because I'm lazy. Right? This is much more memory efficient because I don't have to have 10 function calls on the call stack tracking 10 different integers. Now, for 10 integers, no one cares. But as you can see, eventually your stack overflows and you break. And it just game over. So we do want to be a little bit careful with that. This is a pretty basic one here. Did you guys look at Fibonacci in 150? Okay, Fibonacci is one of my favorite number sequences because I'm weird like that here. So this is fib, because I don't remember how to spell Fibonacci here, of the nth term. So Fibonacci is very easily defined here. Fibonacci sequence, here we go. Let's find our Wikipedia page for Fibonacci. Okay. It says, if nth is 0, the value is 0. If nth is 1, the value is 1. For anything other than 0 and 1, the value of nth is the value of n minus 1 plus the value of n minus 2. Here's my base case. Here's my recursive case. Right? I can approach the base case. Eventually, n will hit 0 or 1, guaranteed. Right? So I can say, hey, if my nth is equal to 0, turn 0 here. Now, you could actually get cute here and you could say, or nth equals 1, return nth. I think that's cute here, right? Because if it's 0, you give back 0. If it's 1, you give back 1. I think it's clever rather than having two ifs here. Sure, I don't know. I thought it was fun here. That's my base case, right? Base case. If it's not that, return fib of nth minus 1 plus fib of nth minus 2. Mathematical definition. Boom, done. We have Fibonacci. We've solved it. Good news. The problem here is, though, for int number, oh goodness, 0 number is less than, let's go to like 45 or so here. Number plus plus. Let's see out this is the number, nth, right? 0th, first, second. TH is probably the wrong value here, but I'm too lazy to fix it here, right? And then there'll be fib of nth. I'm sorry, fib of number. Sorry. There we go. Okay, so we'll get 0 and 1 and 2 and 3 and 4 and as we go. Now we're going to see what the problem is real fast here. Again, forgive the TH. I feel really dumb now, but that's okay. It went really quick, and now it's starting to slow down. I'm at 267 million, and it's really slow here. Now, it's not using a whole lot of memory, right? We're pretty level. It's not using a lot here. It's not like it's eating memory. We don't have a memory leak here, but it's slow. Because what it's literally doing is when you ask for fib of 40, or 44 we were at, right? It says, okay, well, what's fib of 43 plus fib of 42? Fib of 42 says, okay, well, what's fib of 41 plus fib of 40? Fib of 41 says, what's fib of 40 plus fib of 39? The only number we ever add up is 1. So you have literally 444 million ones that the computer has just added, right? Because it was 1 plus 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 1, right? This is terribly inefficient. So I'm going to call this one bad fib here. How about that? This is bad fib. Okay. So just because we can do this with recursion doesn't mean we should. Right? There are better ways to do things. So one of the ways to do this better here, this is better recursive fib that takes an int nth, is to use what's known as a helper function. So I don't want someone to give me more information than they need to, but what I want to track is what the previous value was and what the current value is. Right? If I know those two things, I can add up instead of adding 1 50 million times or 500 million times, whatever it happens to be. So you can write a helper function that is recursive here. So you still get the base case here, but then otherwise we get the helper case. We're going to return this is, I don't usually make it like a private function if you're trying to hide this sort of thing here. We don't want people calling this one directly. Here's the helper recursive fib that takes an int nth, an int for current nth, an int for previous, and an int for current. Okay. So you can say, hey, if my nth is equal to, if the current nth is equal to the nth that I want here, I can return current. I got there. Here's my base case. So this one now has a base case. I've counted up to the correct value here. So you should probably actually let me reverse this order here because it's going to bother me here. So, hey, I'm currently at number 3. I want to get to 3. Great. Well, here's your answer. If we didn't, then I need to recurse. Otherwise, then I'm going to return my helper recursive fib of current nth plus 1. Right? Go to the next one here. Nth stays the same. The previous is now the current, and the current value is now the previous plus the current. Right? We do a little bit of arithmetic. Right? Go to the next one here. Here's the sum of the previous 2. Right? Sum of the previous 2. Sum of the previous 2. Sum of the previous 2. So eventually now, my better recursive fib here will either hit the base case or return the helper fib. Now with this one, my current nth is going to be, I'm at 1, right? The nth is still the nth, the previous is 0, and the current is 1. right? It's not 0, it's not 1. If I wanted to get the nth of 2, right? Well, then it has to make sure I add, right? It has to make sure it runs at least once, right? So you don't want someone to have to call this and tell you, hey, you're starting at 1, here's 0. Well, that's just not friendly. That's not a helpful application. You want to make your functions nice and easy to use, right? Hide away all the details, that abstraction idea. So I want to make this nice and helpful. So this way I can use, and instead of bad fib, I can use better recursive fib here. And this one now actually runs fast. Boom, we get our answers like that. Not hard to add up. The computer's really good at that. It's really slow at adding 1 700 million times, right? So, but if we've done this, right, all we really did was a loop, right? All it's doing, and they call it this tail recursion, essentially. We're just replaced a loop with recursion. So it's less efficient. So you can do an iterative fib that takes an nth here. And essentially we do this same logic here, but we're going to loop. So we're going to say, and our base case is still the same, right? This we know the answer here. Otherwise, now my current nth equals 1. I'm sorry, int current nth is 1, int previous 0, int current equals 1, and while my current nth is less than the nth, let's go take, now previous will equal current, but I can't do that yet, right? So I need to say, hey, I have an int for next is my previous plus my current, right? Then I can say my previous equals the current. Previous, no, my goodness, equals the current, and current equals the next, and then current nth plus plus, right? So figure out what the next value is, add them up, and go. Why is this one not blue? It should be blue. That's weird, right? Eventually, when we're done, we're going to return current, right? Right. Make sense? So now this one, it works. It's not going to look any different here, but this is going to be slightly faster. They don't have, 40 recursive calls on the call stack, right, that I have to track here. I just have one loop as I go. And I should get the same values, right? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. That sounds right. Yeah.
So what was I mean for the better recursive?
So So it's just saying, here's my base case, 0, 1, I know. Otherwise, start using this helper one that needs more information because it's not friendly for someone. So I know, hey, starting at 1, your current value is 1, your previous value is 0. You count up from here in this loop where it's going to be saying, okay, n goes up by 1, right? So it's recursing until my current nth equals nth. I'm going to keep on recursing up. So that's where the recursion happens here. So this one's technically not recursive. Its helper function is recursive, right? So it's not recursive itself. Its helper function is, right? So, but because it's doing a helper function that is recursive, we will still consider this function recursive. Again, ideally, you hide this as a private function here.
But this is the one that actually works.
Yeah, this is the one that does it fast.
Right.
Yep. But again, it's the same as a loop here. Now, this is 3 lines of code, 4, 5 lines of code versus what is this, 10 lines of code? Sure, we wrote less code. Yay, party for us. I don't know. If you're into that sort of thing, go for it. Whatever. So that's a quick definition of recursion here. This is a quick way of looking at it here. So we've got the countdown example, we got the Fibonacci example. Now, just because you can solve a recursion doesn't mean you should, right? These are bad ways to use recursion, okay? Because it doesn't need it. It's just a loop. That's nice and easy here. There's a really famous problem called the Tower of Hanoi. This is animation here. So the idea with the Tower of Hanoi is you have these disks that you have to get from one peg to another peg. We're going to do 3 pegs here. No, get solution. There we go. So let's do 5. 5 is probably easier here. So get. There we go. So with 5 disks, you want to move them from this peg to this peg. But the rule is you can't put a bigger disk on top of a smaller disk. So to do this, well, it's really hard to move 5 disks. But you know what's easier than moving 5 disks? Moving 4 disks. Oh, well, it's really hard to move 4 disks. You know what's easier than moving 4 disks? Moving 3. Oh, well, 3's hard. What's easier than 3? 2. 2's hard. What's easier than moving 2? 1. I can move 1 disk from here to here. Then to move 2 disks, I just move the second disk to the other peg and move the first disk back on top. To move 3 disks, okay, well, put the third disk here, move the 2 from here to here. Well, 2 is hard. I can move 1. 1 is easy. Let me move 1. Now let me move 2. So this is a natural recursive solution, recursive problem where it's hard to do many, but it's easy to do one. So we just work our way up, and the call stack manages all this for us here. So the animation is really cool, right? Just kind of moving over. It moves 1, and then moves the second one. You put the first one on top. Okay, now we moved 2, but now let's move the third one, and then put the 2 back on top. Now we'll move 4, put the 3 back on top.
So your recursive function will just handle this one time and then you just keep on calling
It
it?
just keeps on recursing. Yep. Yep. So we can Google this one. This is a really common. This is Tower of Hanoi, C++. There's a pretty easy solution here. I don't know, Geek for Geek. Sure, why not? So they say, okay, if n is 1, move it. If it's not 1, move n minus 1, swapping what we were doing here. So your auxiliary, your storage, and your so S, A, and D are stupid variable names. I hate when people do this, right? Why is you say auxiliary here, but you don't spell auxiliary here? Like, don't be dumb. Okay. But it says, okay, do that, then move 1, then move the other ones. So if when it was 5, say move 4, move the 5th, move 4 again. Well, 4 was hard. Okay, let's move 3, move the 4th, move 3 again. Right? That's all. So this is really easy with recursion, right? It's only a couple lines of code. Right? There's more comments in this than there is code because they have to tell you what A rod means and what D rod means and what S rod means. Be better. Okay. This is why I hate comments. But you can also solve this without recursion. Without recursion, right? This is much harder. Okay. To do this without recursion, you have to track all sorts of other things here. We have this list of things that we're doing, or our array of things that we're doing. We're moving things off the array. We're adding things to the array. We're like, holy crap. You can do it, and this is technically faster. Right? It has to store less things in memory. Now with 5 disks, it's not a whole lot of things in memory, but you can get up to 100 disks, whatever nonsense you want to get up to here. Sure, it's slightly faster, right? But writing this is awful. Right? I wish this upon nobody, right? So that's when recursion makes a lot of sense. Like with our file structure system, I could make a list of folders and then go into each one of those things that I find in the list here. That's doable, but it's a lot harder than saying find everything in a folder if it's a folder recurse. Right? That's one line versus a bunch of lines trying to track all this. And that's what we're having to do here with this array, have your elements and all this other weird nonsense here. So it doesn't really make sense as a solution here to do it without recursion. So our rule is anything that can be solved with recursion can be solved without recursion. Sometimes it sucks. A lot of times it sucks if that problem was naturally solvable with recursion, like our file structures, like the towers of Hanoi, like some things we look at here. But not every problem that can be solved iteratively without recursion can be solved with recursion. If it's not a loop, there's no recursion. There's no function call happening here, right? So that's all. So like every square is a rectangle, but not every rectangle is a square. Every problem with recursion can be solved without recursion. But not every problem without recursion can be solved with recursion. So a lot of times once we introduce this, people want to use it all the time, and it really just doesn't fit. That's all. Okay. So now I want to look at another case. So this was all just some basic recursion. Now I want to look at backtracking recursion. There's a really fun way of using recursion in a small scale, and it solves mazes. Is one thing you can do with backtracking recursion. We'll do a bunch of them as we go here, but the maze solving is kind of fun here. So the idea with this is I need to identify a base case, and I need to identify how do I approach the base case, right? So let's go and make a little class here. Let's make a new header file for maze solver. Okay, so this will include vector and using namespace standard, a class for maze solver as a private section, as a public section here. Okay, so to solve a maze, we need the maze solver constructor here. It's going to take a vector of char, a two-dimensional vector. We'll call this the maze here, right? And the idea with this maze is parentheses there. There we go. Okay, so then we have a private vector of char called the maze here, and we'll set my this maze equal to the maze. Okay. Maze solver. What? Did I misspell it? I don't think I misspelled it. That was weird. It was red, but now it's not red anymore. So in my source code, my source file is going to use this, right? We're going to go include maze solver. Oh my goodness, no. Maze solver.h. I don't know why it's so mad at me now. Don't I have maze solver? Did I misspell it? No, I found it. I think my Visual Studio is just dumb. Maybe because I broke it with a Stack Overflow, it's upset with me. But what we would do is we'd build a maze. So, right, so I'm going to include vector. Oh, I think we already have vector in here, right? So I can make a vector. My vector of type char for my maze. And I can use my, yeah, it's real upset here. Hang on. Let me just see if I can like build. Build. Can't open maze solver. Really? Maze solver. Did I spell it wrong? Solve. Oh my goodness, guys! I'm looking at this and I can't spell. This is what happens when type ahead doesn't work. I just break. It's like everything autocompletes for me here. Okay, thank you. That fixed all my lines. All right. So our vector of type char. Now we got to include vector, I guess. Should include vector. Okay. Aren't I using namespace standard? Yes, I am. I have too many here. There we go. Vector of char. Okay, now it's happening. We'll make the maze. So the idea here, we'll say, hey, let's just make this a small little maze. So here's like a bunch of spaces here. If there's a space, we can go through it here, right? And then maybe we have, so that's 5. Oops. Right, so here's the outer vector. Here's the rows, essentially, right? We've done rows and columns with vectors. We had fun with that. Why is that? Sure. All of those are not in line. That's sad. Okay. So maybe we have like an X if there's a wall, right? You can't step through it. So we can assume you can go up, down, left, or right, or north, south, east, west, if you like your directions here. So put a wall there, we'll put a wall there, we'll put a wall there, put a wall there. So maybe this is the start character, maybe the end goal is over here. And then maybe we have a wall over here. Let's go over here and over here. And then maybe there's a wall over here. Doesn't really matter where the walls are, right? So there's 2 different ways we could solve this maze. So we just looking at it, easily we can solve it. But the idea is we want to write an algorithm that can solve the maze. What's the steps it would take here? So when we're solving a maze here, if you're not doing keep your right hand on the wall to get out of the maze, you need a different approach. Backtracking says try something. If it didn't work, undo, take a step back, try the next thing. So if you try up, down, left, and right, and if you get stuck somewhere, you undo your step and go back. Eventually, you'll solve the maze. Now, you're going to have taken maybe the longest possible path to get there, but eventually you got there, right? I'm sorry, there's only one way. If this one we remove, we could do it 2 ways. We'll show that in a little bit here. So to solve the maze, then we go to our maze solver. Let's assume we're starting at 0, 0. So let's write a void solve here that goes and solves, and then maybe we want a void or a string. We can just see out of here. So the void print here. So to print the maze, then we want to say for vector of char row in my maze. I want to see out every character, right? So then for char space in the row, we're going to see out the space here. And I don't want end lines because I want these things to run together, right? I want them all to be touching here. At the end of every row, then I want to see out an end line here. So I can give it a maze and I can print it out. Now we didn't do solve yet, but let's see. Can I give this the maze? Make a maze solver, given the maze, and we'll call solver.print. Right? It should give me my printed maze. I'm going to comment this out for now here because I don't want that to run. Right? That's our maze, right? Again, without any spaces, this is relatively easy enough to see, right? So to solve it, then we need to try something. So what is the base case? Well, we got to the end. Well, how do we know where we are? Well, we need a helper function. Right? I need to know what position I'm at. I don't need them to tell me. We could maybe, but it'd be easy enough for me to do it. So I'm going to have a private helper function here. We'll make this a void for solve that takes an int row index and an int column index. Okay, so given a row and column, now I can start solving it and have something I can start recursing off of. So in this one here, we're just going to call solve given 0, 0. Again, it'd be nice, you find start or something here, but that's okay, right? Not too big of a deal. Okay, so starting at 0, 0, we're going to try, hey, can I go up? Can I go down? Can I go left? Can I go right? If I can, go and do the thing, right? So our algorithm is can go up, go up. Can go down, go down. Can go left, go left. Can go right, go right. And these steps here are recursive, right? When you go up, down, left, or right, we're recursing at that new location. So if you can go up, okay, now you're solving from that new location. If you can go down, now you're solving from that new location. Okay, so we're going to try. So if I can go to a position here, it's pretty easy, but that needs to be a nice little function here. This is, can go, given an int row index and an int column index. So this one's pretty easy to check, right? We don't want to go out of bounds. You can't go to a -1 and you can't go more than the length of a given row, right? So we need to check for those things. We can say, hey, if my row index is less than 0 or my row index is greater than or equal to my maze size, right? The number of rows that I have, right? If I have 5 rows, my indexes are 0 through 4. So if it's invalid here, it's no good, right? Row is bad. If the row is okay, then, right? And I want to say, or my column index, let me bump this down a line here, or my column index is less than 0, or my column index. Now, mazes don't have to be perfect squares, right? Column index is greater than or equal to, so I want my maze dot at the row index dot size, right? How long is that row here, right? If you assumed it was a square, sure, but let's be smart about it here. Let's not make assumptions here. So if those are valid, then right, you have a valid row, you have a valid column, right? Right. Then now, if any of those were true, the whole thing is true because we're oriented together here. So this will be invalid at this point here, right? Or my maze dot at the row index dot at the column index I don't know why type ahead hates me today. Is equal to, or maybe it does not equal a space, right? A space character, right? If it's not a space, I can't go there, right? If it's a space, I can go there, right? If it's X, I can't. Sure, right? Or maybe it doesn't equal X. I don't know. We got options here. Maybe not equal X is okay, but we're going to run into the problem in a minute here. That's okay. That's for illustration purposes. So if any of these are true, I'm going to return false. The whole thing's false. If I didn't return false, I can return true. Now, I think I've complained about this a lot before. If you're just saying if something return true or false, don't bother with that. Just return this thing here, right? But now it's actually not that, right? Because if it's true, we're returning false. So if it's true, you return not true, which is false. Does that make sense? So just save a little bit of if elsing here. Just return the opposite of that. It's invalid. It can't go there. So now my can go up is pretty easy. We're saying, hey, if can go to my row index -1 minus to the column index, right? If I can go up, great, right? If that space is open, let's do it. So to go there, then we're just going to call solve, given the row index, given the column index. I'm sorry, row index -1, right? If I can go there, go there. Right? Now the thing I missed here, sorry, we have forgot our base case. Right? This is the complex case. How do we simplify our base case? If our maze dot at the row index dot at the column index is equal to the end here, character end, we can print. We found the solution. If we didn't find a solution, hey, there's work that has to happen here. Now we can start all of our recursive stuff here, right? Base case, right? Otherwise, go do these things. So, okay, try and solve it, right? Let's go up. This was up, right? This one's down, right? Same idea here. If I can go down, now down is just row +1, right? Remember our 2D rows here, our 2D vectors. And then left then is column. right? So this will be left is column -1, right? Go back a column. Yeah.
Put it down this one.
Well, so remember, we start row 0 is the top row, and then row 1 is the next row 2 is the next row 3 is the next row, because 0 is we don't have an origin. We've got the top left for 0 0. Yep. Just remember how you couldn't beat me at tic-tac-toe. No one's salty about that, I'm sure. My wife thought it was mean to offer an automatic pass if you could beat me. She's like, that's just mean you would even say that, because then you're going to get their hopes up. I'm like, no, tic-tac-toe. Everybody knows you can't win a tic-tac-toe, right? Okay. She also thinks I should let the kids win at games. I don't know. Maybe I should. Candyland is just a pure game of chance. Sometimes I lose at Candyland, but give me a game of skill like chess, and I'm crushing the kids. So I give them rook odds or queen odds sometimes, but so eventually I do lose, but I have to give them odds for it. Okay. So the can go and we solve, right? Let's keep on trying it. So let's go and go and go and go and go. So let's see if we can solve this maze here, right? Now, let's go make our maze. We did a print for fun. We just saw it here. So let's call solve here. And let's see what happens. Oh, stack overflow. We did a bad thing here. So if we just think about our algorithm for a second here, we said, can we go down? Sure, I can go down. Can I go up? No, I can't go up. Can I go down? Yes, I can go down. Can I go up? Yes, up. No, down. Yes, up. Yes, down. Yes, up. Yes, down. Yes, up. Yes, down. We forgot to leave a breadcrumb, right? We're Hansel and Gretel. You got to leave a breadcrumb here so you don't walk on a place you already were, right? Because we have to know where we're backtracking. So when we go to solve here, then we're going to say, okay, if we didn't reach the end here, let's leave a breadcrumb. Let's say, okay, hey, my maze at here then will equal, how about like a dot here for breadcrumb, right? Assign it a dot. We'll change the value, not a double equals here. Assign it a dot. So put a breadcrumb down, right? So now when we run it, we don't find a solution. Now this is the thing I mentioned. We're going to run into problems here. Do you know what the issue is here?
Is it because if it gets stuck in a position, it can't go back?
No, it'll go back here. So if we add a print at every step of the way here for fun, we can add a print here. And I probably want to see out like a new line here, just to kind of space these things out here. Handle. So if we run it now, we'll see it tries. Hey, no steps, one step. Oh, we really replaced S. Sure, that's fine. So we go down, 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 down. Then once we get done with here, we come back. We had nowhere else to go. We had nowhere else to go. We tried up and down. We tried left. Now we're trying right. Up, down, left, right. Up, down, left, right. So we keep trying our positions here. We go down, 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 down. We got to here, but we never thought it was solved because we didn't say you could step on an end here. We said if it's not open, you can't go there. Well, that's not correct, right? It could be if it is not open and not the end, right? Those are things we shouldn't step on here. So we can say if it's not open, this is where it gets weird because we're ORing things together. We want to and that one together. So if it's either the end or a space, then we can go there, right? So if it's not open, oh goodness, maybe it's easier to say, hey, because this is cannot go. So if it's not open, so if you say not open or not the end, is that it? Yeah, we want it to be able to go to E. So I'm sorry, the logic here is just confusing here. So we want if it's not. Let's do this here because this is easier here. So I'm going to say if it is open, right, or it is the end. Here, if it's open or the end, that's what I want here. So I want not that, right? Because this is saying I can't go that way. A little awkward here. I feel bad about this. There's probably easier ways to do it, but that ought to do it here for now. Oh, I can now comment out a print here. Sorry, let me stop that. I comment out the print here. So now we're saying you can step on an end. Hey, we solved it. Here's the path that solved it. Right? We did backtracking. So we got to a dead end and said, oh, nowhere left to go. So the call stack says, okay, hey, you're at row 4, column 0. You tried up, you tried down, you tried left, you tried right. There's nothing else to do. So that call comes off the call stack, and we're right back to, hey, now we're at row 3, column 0. We tried down. Now let's try left. Now let's try right. Nothing to do. Now you're at column 2, right? It comes off the call stack. So you can watch them get added to the call stack and come off the call stack as it recurses and backtracks. Does that make sense? Okay, awesome. So that's some basic backtracking recursion here. Um, I don't want to do too much more because I think spreading out the backtracking will help. We're going to do a different backtracking solution on Tuesday before we talk about templates, and then we'll practice a third backtracking recursion in lab to kind of spread that out so we can do a lot of practice with this here. Does that make sense? Okay. I had a lot of coffee, so I was talking really fast here. But again, the idea, did we reach a base case? If not, how do I get closer to the base case? Well, I'm going to try up, down, left, right. Okay. So how this all works for our project then here is we're going to checkers. We're going to find the longest possible jump, the maximum jump for a given piece in checkers. Have you guys ever played checkers? Okay, good, good. So the idea here is you've got a 2D vector or array. If you like arrays, go for it. I just think arrays are stupid because we have vectors of characters for the board. We're going to assume all the pieces are kings because that makes life easy for us. They can jump forwards and backwards. Tracking that separately gets awkward here. We're going to assume B for black pieces, W for white pieces, spaces for empty spaces. Sorry, that should be single quotes, not double quotes. And we're going to make a checkers solver. Your constructor accepts a board, ensures it's a valid checkerboard, or prints an error. So a valid checkerboard means it's 8 by 8, and all of the pieces are on the same color. I don't remember if they're supposed to be on light squares or dark squares. I don't know if it actually matters. I'm sure someone who cares about checkers will tell you if it matters. I think chess is superior to checkers, and checkers is silly, and I could never beat my grandfather at it, so I gave up. And I moved on to chess because I could beat him at chess, but not checkers. That guy was wicked at checkers. So assume, go and validate it. Make sure it's the right size and all the pieces are on the same color, either light or dark squares. I don't care which one, they're all there. Okay, so we're gonna have a function get max jumps that returns the max number of jumps of any white checker. So for every white piece, calculate the max number of jumps, return the max of those values here. Okay, so 15 points for this one, 5 points for having the constructor that invalidates your board. If nothing actually works beyond that, you still get 5 points, right? Using the 2D vector, then being able to find the max number of jumps for a single white checker. We're going to use backtracking recursion. We're going to try this here. Then 5 more points if you can do for all the white checkers. It's just a little bit of additional logic here. So if we look up a checkers board here, and sure, there's one. Let me grab this. We're going to draw on it all over here. Snip tool. I have to use the tool here because my do not disturb mode's on. There we go. Okay. So if we have checkers on the board here, right? So let's say here's a white checker here. We'll hit a black. I'm going to move over a little more. Sorry. Got a white checker here, a black checker here, a black checker here, black checker here, and a black checker here, and then a black checker here. Okay. So if we just have a single white checker here, right? It can jump this direction for one jump. Okay. It can also jump this direction for 1, 2, 3, 4, and 5. Right? It could also jump this direction 1, 2, 3, 4, 5. So we're going to look at every single possible outcome and see which one was the longest. Right? We're going to backtrack. So we're going to try it. So to try it, you have to change the board, right? Like we added our piece here. So we didn't undo anything yet. So on Tuesday, we're going to look at how we undo the moves, right? Because you want to, once you've jumped, you have to undo that, right? If you jump over the piece and remove it, you jump over the piece and remove it, jump over the piece and remove it. So you might also imagine if you had a second white checker here. What if you had one here? Well, this one can jump 1, 2, 3, 4 different 5, right? Its max jump is 2, right? This one and this one, right? But you don't want to have this one go first and have those pieces off the board. You have to put them back for the next white checker to be tried. See what happens. So we'll look at when you backtrack, you can undo the moves you did. So if we wanted to, we could remove our breadcrumbs. If you wanted to make it look a little prettier, sure, that's an option we could do if we wanted. And then you could show just the path we went on. So to undo our breadcrumbs, right, if we didn't solve the maze, we would want to go and undo this, right? So if we didn't reach the end here, right, at the end of this, then we could go through and set it back to a space. Now when I run it here, I have just the path I took because I undid the step here, right? So I removed these ones on the dead end here, right? So this is the undo step here. Undo, right? Make a move, try and recurse, and then after all the recursion happens, come and undo, right? So we got those options here. So that's what we're going to do with checkers. Um, so you're going to want to try and set up a couple scenarios and make sure it works for you here. Right? Make sure you do the right number of jumps, those sorts of things here as you go, and you solve it for all the white checkers, right? Because you've got other interesting things could happen, right? Make sure you don't jump off the edges, those sorts of things here. Make sure you don't jump over your own pieces, right? You should only jump over black pieces, that sorts of things. So that's the next project. We have 3 weeks because we're going to pretend break doesn't exist. So if you want to work on over break, great. If you don't want to work on over break, great. You still have 2 weeks of class time to work on it now. So I've got to do on the 13th here. So ideally, you can actually take the week off of break and have a good time to recharge and rest, that sort of thing. Okay. Questions, thoughts, concerns? Makes sense? Okay, so we'll practice more. We'll do another backtracking example on Tuesday. I just don't want to throw a ton of them at you all at once because it does get to be a lot here. Get a chance to kind of think it over a little bit. And then maybe we'll get in the templates, maybe not. And then we'll practice it in lab. Next Tuesday, we'll do some backtracking recursion in lab to practice it. It's a simpler thing, but similar to our checkers problems. You've had a chance to practice it, okay? All right, awesome. If you don't have anything else, we'll call it a night. You stay warm, stay safe. Yeah, enjoy the winter. Hopefully you can go sledding.